Okay, let's unpack this incredible technology that literally lights up our digital world dense wavelength division multiplexing, or, well, DWDM.
That's the one.
We've pulled together insights from some key players like Corning, Ribbon, Cisco, JDSU.
Industry leaders, yeah.
And our mission today, really get into how DWDM became the answer to, well, our world's massive hunger for bandwidth.
And it is massive. We're talking about insane growth.
Totally. Like one company saw demand jump 32 times in 1 year.
Which is just staggering.
And think about it, people using the bandwidth equivalent of like 3 hours of data every single hour.
Yeah, the networks were buckling. They called it fiber exhaust. Carriers were hitting basically 100% capacity.
Oof.
So what do you do then?
Well, that's a crunch, right? Faced with these exploding data demands, service providers had essentially two stark choices.
Okay.
They could start digging and laying miles upon miles of new fiber. Super costly. Think an estimated $70,000 per mile.
70,000. Wow. And get this, most of that cost.
Yeah.
It's permits and construction, the digging, not even the fiber itself.
That really puts it in perspective. So digging wasn't exactly appealing. What was the alternative?
The alternative was getting smarter, finding clever, really innovative ways to squeeze more out of the fiber they already had in the ground.
Right. Avoiding all that digging and permit hassle. A lightware solution, you could say.
Exactly. It's not just about the glass. It's the whole infrastructure headache.
And here's where it gets really interesting, because DWDM, well, it offered exactly that smarter path.
It did.
Because traditional ways like time division multiplexing, TDM, SONET and systems like that, they basically increase capacity by slicing time into smaller and smaller bits, sending data faster. Imagine a single-lane highway just moving cars really quickly.
Still just one lane, though. Fast, but limited.
Precisely.
Yeah.
DWDM takes a completely different, frankly, much more elegant approach.
Yeah, what's fascinating here, I think, is that DWDM is like taking that single-lane road and, boom, magically turning it into a multi-lane superhighway.
Without laying any new asphalt.
Exactly. It works by assigning different incoming optical signals to specific frequencies of light, or wavelengths.
Wavelengths, okay, like different colors.
Basically, yeah. Think of them as different colors of light. Red carries this signal, blue carries that one, green another, each carrying its own information at the same time.
All down the same tiny strand of glass fiber.
All down the same fiber without interfering with each other. It's a bit like how different radio stations broadcast on different frequencies, right?
Yeah.
You can tune into one without hearing the others.
That's a great analogy. So this multi-lane light highway, what does this transformation actually mean for us? The people streaming, working, connecting.
It means a truly massive leap in capacity. Just huge.
How huge?
Well, DWDM allows a single pair of fibers to go from maybe 100 gigabits per second GBPs, which was already fast, to over 10 terabits per second, TBPS.
Terabits, that's 1,000 times more gigabits, roughly.
Orders of magnitude more, yeah. And research has pushed it even further. We've seen systems demonstrated with like 128 different channels, each running at 40 GBPs.
Wow, do the math.
That totals over 5 terabits per second on just one fiber. And critically, another big advantage, DWDM is what we call transport protocol independent.
Protocol independent, meaning?
Meaning it doesn't really care what kind of data you're sending. It can simultaneously carry, say, email, video streams, your voice calls, maybe older Sonnet's DH signals, and all the modern internet data like IP packets.
It's all mixed together.
All mixed together over the same optical layer. This flexibility is incredibly important for bringing together lots of different services onto one physical network. Really efficient.
Okay, so the capacity is mind-blowing. The flexibility is key. But what about practical stuff? Reliability. Does it actually hold up in the real world?
Absolutely. That's another strength.
Yeah.
Looking at what Corning points out, the DWDM multiplexers and demultiplexers, the devices that combine and separate these colors of light, they're passive.
Passive, like no moving part.
More like no power needed. They don't need electricity to run or specific temperature-controlled HUDs.
Ah, okay. So fewer things to break down.
Exactly. Fewer points of failure, lower energy bills for the carriers, which ultimately means more reliable data transmission for you. They use really sophisticated thin film filters and special waveguide tech that's, well, stable even when temperatures change.
So it just works hot or cold.
Pretty much.
Yeah.
And this ensures low insertion loss, meaning signal stays strong and high isolation so the colors don't bleed into each other.
Keeps everything clean.
Keeps it clean.
Right.
And these devices are rigorously tested. They meet tough industry standards like Telcordia GR1209 and GR1221. That means high reliability baked in. They operate across the standard C-band and L-band. Those are just the prime spectrums for fiber optics.
Got it. So it sounds like from, your high-def streaming binge to critical financial data transfers, DWDM is the sort of unseen hero.
It really is. Quietly pushing unbelievable amounts of information further and faster through the fiber that connects everything.
Yeah, this deep dive really shows how some clever engineering, just using the different colors of light, completely unlocked all this capacity we desperately needed from the wires already there.
Fundamental shift.
Definitely. So here's something for you, the listener, to think about. We've seen how engineers harnessed light waves as our demand for data just keeps exploding. What do you think might be the next fundamental physical property engineers could tap into to meet the even crazier challenges of tomorrow's networks?